Hi, everybody. Thanks for putting up with this asynchronous Wednesday here. So what I'd like to do is try to finish up some of the drawings that we did on Monday. Um, do one quick little demonstration for you over the camera, and I'll try to bring one on Friday so it looks cooler in glass too. Um, and ideally, try to come up with a way and an explanation of how these global winds work based on the rising and falling of air that we were taking a look at on Monday. Alrighty, so let me share my screen and let me get a quick drink here too. Been cranking out the videos tonight, knowing that I wasn't going to be there tomorrow. Um, oh yeah, share. So, so here's what I'm going to do. Hopefully you guys can see in the screen now. We have we have the awesome globe that we were drawing the other day here. And I'm trying to find my mouse. There we go. Just getting it reoriented there. We have this awesome globe where we talked about at the equator, we had all that warm air that's less dense, so it rises because it gets all that energy from the sun, hitting the equator much more frequently throughout the year. When when you go further north in latitude, you go to those higher latitudes, the energy from the sun doesn't hit at the same angle. It's more dispersed. That light energy density coming in from the sun is more spread out. It's a lower density, so even the light that does hit the ground doesn't impart as much energy. So literally, it gets cooler the further up you go, and that's not even counting the winter seasons, right? When you're tilted away from the sun and the angle is even lower. But we ended up with kind of these cells going up and off of the surface of the Earth. We had the rising stuff near the equator. It would come up, basically hit the troposphere. Let me see here. Let me get my little ant. There we go. That's what I'm looking for. Um, maybe it'll. Sorry, I'm trying to get my mouse. There it goes. So basically, you'd have that rising air at the equator. It hit the troposphere. I mean, the top of the troposphere, which is the tropopause. And then it starts becoming more dense as it cools off, so it starts sinking. And as it starts sinking, that sinking air is literally squishing the air down on top of 30 degrees north right there, give or take. And that creates an increase in pressure. When the rising air at the equator goes up, it's kind of like lifting mass off of the top of you, kind of like if you're wearing a heavy backpack and somebody offered a hand and just kind of pushed up underneath your backpack as you're walking, how your backpack would feel lighter. That's kind of what's happening here with the air is rising, and so it has less force pushing down, and it becomes low pressure. Okay. And so again, up at 60 degrees north and 60 degrees south, just to recap, we had low pressure rising air there just because that air at 60 degrees is relatively much warmer than the air that's at 90 degrees. So you kind of get this upward motion. And some of it goes to the South Pole and back down, and some of it goes up to the troposphere and ends up at 30 degrees north. Excuse me, 30 degrees south here as well. But remember, dense cold air sinks, which makes high pressure. Low pressure is rising air, and that's a big deal. When we left on, when was it? Monday. When we left on Monday, I showed you a quick little video clip about the Coriolis effect. And so I want to take a quick minute and kind of show you that again, and then add an interesting demonstration. Add an interesting demonstration with this little water bottle here in just a second. All right, I'm back. Sorry. Had a runny nose there for a second. Share back to this one. There we go. So we saw at the very end of Monday this Coriolis effect. This guy trying to predict what was going to happen if the ball was going to spin. So let me show you that really quick, just as a recap, and then I want to show you why that's important and how we're going to apply that to us here in just a few minutes. Actually, you know what? Nope. I want to do the cloud in the bottle first, then we'll come back to the Coriolis effect. So let me stop this. Okay. So I'm gonna do my best to kind of hold this in my body, in front of my body, so it doesn't disappear behind my background. But it's just a Gatorade bottle. There we go. It's a Gatorade bottle with some water in it. And then I'm gonna uncap this. You guys can see there. All right, so I'm gonna uncap this sucker. I'm gonna take a match. I'm gonna light the match. I'm gonna drop it in here so that it adds smoke particles into the bottle here. And the reason I want smoke particles in the bottle is um, water cannot condense around nothing. So it has to have small particles, something to glob onto. And that's what these smoke particles are going to do. So check this out. Hopefully. Oh, this looks like a weak. That match didn't have any white stuff on it. Well, I got it enough to almost smoke and start going. It smoked, but didn't go. Let's see here. There we go. Okay. So I'm gonna let this burn for a second. Woo! Got my finger just a tad. All right, I put the match that's in there. So now there's some smoke. I'm going to kind of swirl around the smoke. And what I want you to see is there's water in here, there's air up here, and in this air, there is quite a bit of moisture. All right, there's water vapor that's in there as well. So just by doing this, I've kind of saturated the air that's inside this bottle. So watch what happens here is I'm gonna squeeze it really annoyingly for about 30 seconds to make some noise. So I know everybody in my family's already going to sleep, so hopefully this doesn't wake them up too bad. Door's closed. But I'm gonna just squeeze this back and forth like 30 times, 40 times, and then we'll see what happens in here. And maybe you can kind of judge what happens based on if you can still see my shirt and my sweater beneath it. So you ready? I'm gonna start now. Maybe I'll put the microphone over there so it's not quite your. Right. So I don't know if you guys can see. You can see my shirt pretty well when I squeeze, and when I let go, it fogs up. You can't see my shirt. So shirt, not shirt. Maybe you can see it go back and forth here. I know there's a light on there. Let's see if I can make the light shine on a little bit better here. So no cloud, cloud, no cloud, cloud, no cloud, cloud. So this is a cloud in a bottle. It'll work with any like soda bottle, Gatorade bottle, 2 liter bottle, water bottle, and it does look more cool in person. All right, just so you know. But there's an important thing that I want to apply to our drawings with this. Get that back up here, and that's this. So let me go back to sharing my screen. Man, I got my thumb good there. Wasn't paying attention to that match as close as I should have been. Oops, wrong one. Wrong screen. This is the screen. Okay, so back to our Coriolis, or not to Coriolis, but to our air pressure drawings over here. So I'm just going to reorient my mouse, get it over there. So this area where it says low pressure, this is rising, warm, less dense air. I want you to think about when I was just squeezing the bottle and letting go of the bottle, which of those two times, squeezing or not squeezing, did the clouds form? And so if you can't remember, squeeze the bottle, the clouds went away. When I let go of the bottle, the cloud came back. Okay? And so literally letting go of the bottle, that's low pressure. I'm releasing the pressure on there. And when I release the pressure, what that does um, is it lowers the amount of energy that is in the bottle. So when I squeeze it, I increase the energy in the bottle. When I let go, it decreases the energy, which kind of in turn lowers the temperature. And so when I do that, it caused all that water vapor that was saturated in the air to glom onto the little smoke bits. And so how does that relate to this drawing that you're seeing in front of us? Well, I'm glad you asked. I'm glad you're having questions about it anyways. Basically, what this means is anywhere we have low pressure on Earth, this is where we get clouds. Okay, so I'm trying to draw some clouds right here. I don't know if this is the best looking cloud, but you get the idea. So there's some clouds. So low pressure is where you'll find the clouds. It's also where you'll find, you got clouds, generally speaking, right? That's where you get the precipitation and the rain. So low pressure, think of that as like letting go of the bottle, not squeezing the bottle. And maybe I'll write this off to the side here just so you guys have something to think about. Um, oh man, it's really thick. Let me fix that for you. And I'll make that even skinnier here. Okay. So I'm going to say that the clouds form in low pressure. And we'll see why this is. But basically, when you have this low pressure and this rising air, it cools the air a lot more. And that cooling allows the condensation that going from a gas to a liquid, those water drops, allows that condensation to happen. All right. So the clouds form in low pressure, and this would be like, I'm going to say releasing bottle. And I know I'm writing over the top of the tropopause and all that good stuff, but so the clouds form in low pressure areas. It'd be like the analogy here is like me releasing the bottle. So this is not the only place where you'd find clouds. So I kind of drew clouds there. I'll maybe draw a little bit more. So anywhere you find low pressure on the Earth, that's where you're going to find the clouds. So let me scroll up a little bit more. So here's my other low pressure at like minus 60 degrees. So if that's the case, well, I'm going to draw my clouds right here. That's not very good clouds, but you get the idea. All right, so there's some clouds right there. Here's my rain, 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 rain. So again, low pressure, rising air, that causes the condensation because the air is cooling as it's rising. It's losing energy as it rises. So there's that. And then dun, 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 we also have at 60 degrees north, same thing. So I think it's worthwhile drawing the clouds up here just so you remember. I am no Bob Ross, but I guess when I can take my time, I can make it a little bit better. But I don't want to make my drawings super, super great, right? All right, so anyway, there's another cloud right there rising above 60 degrees. And that is a very, very large cloud, comparatively speaking to the rest of the stuff that's there. Okay, so there's our cloud. Now, that's where the rising air happened. Conversely, that high pressure, that sinking air, the reason I had us write high pressure on there on Monday is it's like when I took the bottle here. Remember, I took the bottle. When I squeeze the bottle, the cloud disappears. When I let go, the cloud comes back. Gotta, so probably needs a little bit more. I think the smoke got trapped in the water now, precipitated out, so I'd have to add another match. But basically, when I squeeze the bottle, the cloud goes away. When I let go, the clouds come. So high pressure would be like me squeezing the bottle. All right, so go back and to our deal right here. So if that's the case, we have this high pressure, this sinking air. And so this is going to be like associated with dry areas. So the opposite of clouds is dry. So if the clouds disappear, there's no rain. It's going to make things dry. So how am I going to have you guys demonstrate this? Well, I think an easy way maybe is something that's only found in like certain deserts in the world and not all of them. But uh, I'm just going to draw a little cactus right here, like a saguaro cactus, just to represent that that's dry and that's hot. Or if you want, maybe you can add a little um sun. I don't know what would be a good thing for hot. Um, I don't know. Here's sunny. Okay, so a sunny desert with a sunny sky with uh, a cactus there or something. All right. So the cactus is trying to be my representation of, hey, it's dry. Okay. So high pressure sinking air. So the other thing I would write underneath here is that I'm going to say, oops, I'm going to make my color different here. So if we have high pressure sinking air, it's going to be generally dry. And, could be hot. Doesn't always have to be hot, but that's one of the things that usually happens, that sinking air compresses and heats as it sinks. So it generally makes it hot. And then when we have low pressure or rising air, excuse me, I had a little hiccup there. It's generally um, wet, like I guess, generally wet and usually a little bit cooler. Okay, at these latitudes up north. And then down at the equator, let's see here. Down at the equator here, it's also going to be generally wet, generally wet, and in this case, also pretty hot down at the equator. Okay, but that heat is from the heat energy smashing down on the equator. It's not from sinking air up above. Um, okay, so what else do I want to say about that? Generally, got that, got that. Oh, I know. I think, let me stop sharing here. Maybe. There we go. So actually, I want to share a different screen. That's what I want to do. So I want to go to Google Earth here. So I think I mentioned this to you guys really quick before we left on Friday or Monday. Jeez Louise. Let me reorient myself there. So there's north. You can see some clouds. Here's North America right here. I'm going to go to View, Show Grid Lines, so you can see where my latitude is. So here's the equator. But I just want you to kind of see where the equator is, very similar to what we just drew. Hey, that equator is very green, and that's because it's very wet. And that's where you get those rising low pressure centers most of the time. For the most part, that pattern is true in Africa. All right. It's true in the central regions of the equatorial regions of the Pacific and Asia. Um, and it kind of goes around similarly back to the other side of the globe. Whereas if I go over to here, and I think we ended on this yesterday, Monday, if I go up to about 30 degrees north, give or take, which is right here, kind of in the middle, you see these big, huge, massive swaths of desert. That's where you generally have the air kind of sinking and compressing down and drying everything out. You move north of that again, get back to that 50, 60 degrees, give or take, and things start greening up again, especially right around here. It's really obvious in the northern parts of Russia here. You get that tundra that has lots, and not just tundra, but the boreal forests that are up there that grow and take advantage of the long summer light. And it's super green. And you can see, hey, 30, 40 degrees, give or take, it's also pretty dry right around there. And we're going to talk about some other impacting factors like the mountains and stuff a little bit later on. But if you go to where we are in North America, you can see that right around 30 degrees north, the trend is bucked a little bit up here. It's kind of green in the eastern US at that latitude. Um, it's drier at that latitude as it should be, like where we are. But there's some extenuating circumstances, again, with mountains that are going to cause a little bit of different patterns than what we might expect otherwise. But if you go back up into the 60 degrees at Canada, look at that. All green, very wet up there. Okay. So I would show you more stuff down here. I can show you down there. Here's Australia. You can see most of Australia is right around that, 20 to 30 degrees south. That part is pretty doggone deserty. And then as you get closer to the equatorial regions, or you get further north, uh, or excuse me, further south, you get wetter regions. And same thing with New Zealand. So how in the heck that squeezing bottle, right? I showed you the high and low pressures, which kind of gives us a general idea of where we would expect wet and dry. How in the heck then does that wet and dry look like? What does it look like on an Earth that is actually spinning? All right, so what we were just drawing, I can go back to my share screen here. Wrong button. So I go back to the drawing we were looking at. This drawing here, all of this is a generalized, like perfect view of Earth. If the Earth wasn't spinning, um, if it was flat, if there were no mountains, this is kind of the convection cells that we would have. And those convection cells would be kind of in a three-dimensional surface all the way around. So you got to imagine like these rolling tubes of air that would go around the whole entire equator there. All right. But our Earth is not stationary, it is spinning. So let me go back to the Coriolis force now, the Coriolis effect, which is the apparent deflection of wind, or well, I should say fluid, so it could be air or water on big enough bodies because of the spin of the Earth. So here's how that looks and how that works. Oh man, it's late. I keep hitting the wrong buttons. I apologize. So let me share my sound. Give you a stereo high fidelity stuff here. Okay.
With a simple game of catch, I think I've found a way to show an effect that will have you doubting your very own eyes. Now, they don't know it yet, but our budding ball players sitting on our specially rigged merry-go-round are about to demonstrate a rather astonishing optical illusion.
Right, here's the game, right? You're going to throw the ball straight to, what's your name, Victor, right? Yeah. But this time, I'm going to complicate things slightly. I'm going to rotate the merry-go-round counterclockwise. So you throw it whilst it's moving. What's going to happen?
I don't know why, but I feel like if we're going fast enough,
yeah,
like I might actually be the one catching the ball.
Okay, so you're going to throw it and you're going to catch it. All right.
Yeah, I don't know.
Right, what's going to happen, dude?
It's going to veer off to the left.
So the ball is going to swerve off to the left.
Yep.
And you might catch it.
Possibly.
Okay, good. Right, so what's going to happen?
I think it's just going to come straight to me, and I'm going to catch it like the champion that I am.
Show me the catch. Okay, great. Right, okay, so everyone, no, hang on, one more. Spencer.
He's not arrogant.
Just quietly
He's
confident.
not catching it. He's
Really?
not catching it, no.
So what's going to happen to the ball?
I'm catching it. It's right here.
Great, so we've got one saying to go off to you, one saying to come to you, Spencer, and you think it goes straight ahead, but you think you'll be the one catching it.
Yeah.
Now remember, the ball will be thrown straight across the spinning merry-go-round, but where will it end up? Will it be caught by the thrower? Will it be caught by the person opposite? Will it be caught by the person to the thrower's left? Or by the person to the thrower's right?
Right, in your own time, throw the ball.
I got this. Oh!
Whoa!
I told you it was gonna happen.
So the answer was D. It was caught by the person on the thrower's right. Our camera angle seemed to show the ball bend in the air. So is that a camera effect, or are we seeing what they saw?
Hang on, this couldn't get much more simple. The idea was just to throw the ball straight to
Here's
Victor
where it
to
gets
show us
crazy.
his amazing catching skills.
That's right.
Yeah, I did. It just curved right over this way.
So let me get this straight. So somehow you threw the ball, it left your hands, and then what?
And then it just got sucked over to him.
In the air.
Yeah, I threw a perfect throw.
What did you see?
Yeah, curved right in.
Right, so we're all agreeing here the ball curved in midair.
Yeah.
Yes.
And you didn't cheat this at all?
No, I didn't.
Okay. And do you know why it did that?
No.
Nope.
No idea.
It's called the Coriolis effect. And it's very simple. It's objects in motion appearing to be, it's an optical illusion, appearing to be deflected off their intended course. So what's actually happening here is you are throwing this ball. You can only throw a ball in a straight line. Can I clear that up?
Just kind of watch this. I'll let you pause to think. So that I think the blue dot is representing the lady right here, and the red dot is supposed to be the dude over on the left-hand side of the screen. So she's trying to throw it straight across to the dude sitting across from her. But because they're spinning, she's going to throw that ball in a straight line, and that ball is going to continue straight. That's just how physics works. But watch what happens as the merry-go-round keeps turning. Literally, the people are going to be rotating around underneath
straight
them.
away.
Yes.
Even though it appears in your eyes to be bending. So you throw the ball straight, it's still going straight, but the table is moving below you, and all of a sudden, look who's in front of that straight moving ball, and it looks like it's bent off to the right because you're still.
So that's the apparent trajectory, okay? So when it gets deflected and moves like that, that is what we call the Coriolis effect. Now, for fluids, it only works on very large areas, like ocean scale, maybe Great Lakes scale to some extent, and the atmosphere, which is really big. So we're going to kind of keep it simple and not go too crazy with it. But let me show you kind of how this works with Earth and why we really care. All right.
Imagine you're a cloud that formed here on the equator. You'll have the same velocity as the Earth, but then a gust of wind sweeps you to the north where the Earth isn't spinning as fast.
So this is important. Why isn't the Earth spinning as fast up there? And so give me one quick second. I'm going to pause this and I need to get some numbers out so we can do some calculations really fast, so I don't have to bore you with that. And then we'll come back to it just a second. Oh, come on, pause. Go. Okay, so I did some quick calculations here and I want to show you what the actual numbers are, and then we'll get back to that little video clip. Let me go back to here. So down at the equator, just looking everything up. So the equatorial circumference, I'm looking over on the left-hand side in this bit right over here. Oops. Gosh darn it. Let me get my, okay. So down in here, this is what I'm talking about. The equatorial circumference. So how far would it take if you had walked all the way around the equator, assuming the Earth is a perfect sphere here for these calculations, which it's not, but we know the distance around the Earth at the equator is 24,857 miles, give or take. Okay? So if you were that person that we talked about earlier, standing underneath our rain cloud here now at the equator, if you're that person, literally rotating around the Earth's axis once every 24 hours in order to go all the way around the globe once, rotate around that axis once in 24 hours, you would be moving 1,035 miles per hour. So if you're standing at the equator, you're moving at 1,035 miles per hour just by standing still on the equator as the Earth rotates. Kind of something people don't really think about, right? Now, if I go up to 30 degrees north, all you have to do is some simple geometry. You take the cosine of the circumference there. And so the cosine of, cosine of 30 degrees, sorry, cosine of 30 degrees. And then you multiply that times the equatorial circumference, and it comes up with 21,377 miles. So the important thing to know here is at 30 degrees north, give or take, the distance around the Earth is only 21,377 miles if you stayed walking along the 30 degrees north latitude line. So that area, if you're standing at 30 degrees north, which is about where we are, give or take a few degrees, and you divide that by 24, that means folks where we're at are only going about 891 miles per hour compared to the screaming fast equatorial region, which is 1,035 miles an hour. So that's what 150-ish miles an hour difference. All right, that's a pretty big difference. So why do we care? Well, let me show you. So here's why we care, and then we'll get to the drawing, and this will be kind of the last thing. Maybe.
Due to inertia, your speed remains the same. You don't get any faster, but everything around you is literally traveling slower, so you, relative to the ground, move ahead of everything else. If you're a cloud that forms at the slower, so you is the same spinning as fast.
So these arrows are representing, the big arrows are representing fast spinning at the equator, 1,100 miles an hour, give or take, or 1,035 miles an hour, versus these smaller arrows are kind of representing that 891 miles per hour. Actually, this is even going to be slower, 60 degrees north. That's probably going to be closer to 500 miles an hour. All right. But anyways, you're going from 1,000 to 500. you maintain that velocity. So like you have that inertia, you're staying at that speed. So as you drift north, if you go north, you're going to be going really, really fast over the top of things that are not going as fast underneath you. So what that does is give
Fast.
you
Due to inertia,
this apparent motion of you going in front of
your speed remains the same. You don't get any faster, but everything around you is literally traveling slower, so you, relative to the ground, move ahead of everything else. If you're a cloud that forms at the 45-degree line, you'll also have the same speed as everything around you. But
if you go from north to south now, you're going slower, getting into the faster stuff. It's like if you hopped onto a treadmill that was already running, you're going to kind of get flung off because you're not going as fast. So here's what happens here.
if you drift down to the equator, you'll be moving slower than the ground underneath you, so you'll fall behind. And the same thing.
So I'll play it again.
Imagine you're a cloud that formed here on the equator. You'll have the same velocity as the Earth, but then a gust of wind sweeps you to the north where the Earth isn't spinning as fast. Due to inertia, your speed remains the same. You don't get any faster, but everything around you is literally traveling slower, so you, relative to the ground, move ahead of everything else. If you're a cloud that forms at the 45-degree line, you'll also have the same speed as everything around you. But if you drift down to the equator, you'll be moving slower than the ground underneath you, so you'll fall behind.
Okay, so now I'm going to go back to here. If I pause it on this part, if I start from the equator and I go to the north and you follow that red line, okay, if I were trying to go straight north, like this cloud was trying to go straight north, but because it had so much speed, it would kind of moved ahead of everything else relative to what was on the ground, it looks like it's been deflected to the right. So see how that red line looks like it started from the equator, and if you were to draw an arrow on that, the arrow looks like it's curving to the right. Okay, that's something to know.
Ground move ahead of everything else. If you're a cloud that forms at the 45-degree line, you'll also have the same speed as everything around you. But if you drift down to the equator, you'll be moving slower than the ground underneath you.
Okay, so now the same thing here, and I want to show you this. Let me get my little, where's my stinking, there it is right there. I want to make a different color so you guys can see it on here. So this cloud wanted to go straight down like this. That's where it wanted to go, but because it was moving slower, it got deflected and kind of fell back behind. And so here's the thing I want you to think about. It wanted to go that way, but it ended up going this direction like so. And so I'm going to ask you right now, and I want you to think about it. Which direction did this get deflected to? Like if you were in the perspective of that cloud. So I want you to imagine if you stood right here and you were walking on a map going this way, and all of a sudden you ended up kind of ending up over here when you were intending to end up over there. If you were walking downhill here, you would be deflected to your right. I should say south in this case. You'd be deflected to the right. So if you were walking down this way, if you were walking this way, this would be to your right. That is to your right, okay? So even though I'm drawing arrows that are pointing left, if you're in the perspective of this person walking this way, this would be their right-hand side as they walked this way. As opposed to, it's easier to see on the first cloud moving up. Okay, so let's go back to that first cloud moving up again. Okay, so this time you can totally see it makes a lot more sense seeing it maybe from this perspective that the cloud wanted to go straight up north, but because it was moving so much faster, it kind of pulled ahead and ended up in front that way. And so it ended up being deflected or deviated to the right. Okay, so it wanted to go straight or north, but ended up being deflected to the right a little bit. So here's the big thing. No matter where you are on Earth, in the northern hemisphere, you get deflected to the right, and the opposite is true in the southern hemisphere. You get deflected to the left. So if I were to start here and I was trying to walk straight down like this, going down there, I'd be deflected to the walker's left or the cloud's left, going that direction. Okay, so let's apply this to our drawing and we'll call it good and get to the circulations on Friday here. Okay, so gotta find the right sharing again. Boop. All right. Oops, wrong one. Nope, I'm on the right one. Sorry. I got my screen messed up here. So I'm going to draw a series of dotted kind of lines here. Let's see, there we go. Come on. Trying to get my, there we go. All right, so I'm going to draw a series of kind of dashed lines showing where the air wants to go based on what we're looking at here. So if you remember on the side of our drawing, over here on the left-hand side, right here, this is where I'm looking, okay? We can see we have these arrows of wind filling in that convection cell. So as that low pressure had that rising air, you had more air coming in from the bottom to fill the void, basically. All right. So that air, what ends up happening is if we were to draw this like from an airplane view drawing down, that air on a non-spinning Earth, let me get my red here, the air on that non-spinning Earth is trying to come to the equator like so. Okay. And I can say the same thing on the opposite side as well. Man. Okay. So it's trying to come from, if we're following these arrows right there, it's trying to come up like that to the equator. Or in this case, down from the equator, going like that. And I'm drawing dotted lines here to represent that's what the air wants to do. And it's doing that all around the whole entire latitude there, this whole entire region. And how do I know they're going down? Well, they are coming to the equator to then get warm and then rise up. So you got to kind of imagine in this area right here, this would be air coming straight at your face out of your monitor that you're looking at right there. Okay. So I just showed you in that little video clip just a few seconds ago, there's a couple of rules that we need to know. And that is this. Oops, stuck on it. All right, I'm gonna kind of write this somewhere else. Is that in the northern hemisphere, there we go. Northern hemisphere, sorry. In the northern hemisphere, Coriolis deflection, and that's that apparent spin, that Coriolis deflection there. All right. Coriolis deflection is to the right. Okay, so if it helps you to abbreviate, so northern hemisphere equals right. Okay, so the northern hemisphere is always deflected to the right. So ocean currents, uh, atmospheric currents deflected to the right for the most part. Okay, and it's flipped in the southern hemisphere. So in the southern hemisphere, it's backwards, and I'll go down over here. It's not backwards, it's just opposite. So in the southern hemisphere, so I'm going to say the southern hemisphere deflection is to the left. So if you're fans of old school Beyonce, right? She must be southern hemisphere focused because it's to the left, to left, to left. So, or is it to the right, to the right, to the right? I can't remember. No, it's to the left. Yeah, to the left. It's been a while. So yeah. So anyways, you can kind of southern hemisphere is to the left. Okay, so those are some things that are important to remember and think about and know for this. Okay, so back to our arrows. Here is our arrows in the northern hemisphere. We're looking at this one right here now. Okay, so the air wants to go from north to south, coming towards the equator to go rise up. It wants to do that. But remember, everything in the northern hemisphere gets deflected to the right, okay? And so if I am going to draw this, and if it helps that you can turn your paper upside down, I don't really care. But if you put yourself in the position of a person, all right, walking, And like the person's going to be that's shoulders. That's supposed to be shoulders right there. This is going to be the person's left. This is going to be the person's right because they're going to be walking forward going like this. If we get deflected to the right, which is, here's my right, here's the person's left, if they were walking, as they try to go down this dotted line, they're going to get deflected like this. Okay? And it doesn't matter anywhere you go in that region between 30 degrees north and the equator, everything's going to be deflected to the right because of the Coriolis effect. And conversely, oops, doggone it, everything, geez Louise, everything in the south is going to be deflected to the left, which is going to look like this. So you start at the tail end of the arrow, and if you were trying to follow the path of that arrow and got deflected to the left, so like if you were the person here, here's your shoulders, here's your left, here's your right, you're going to be deflected over there that way. Okay? So, we'll come back to that in just a second. Actually, I'm going to show you right now. So what this means and what happens here is if you were to draw this a couple more times, right? The air wants to go north like this, and over here it wants to go south. Let's see here. It wants to go south again, right? So the actual airflow is the thicker arrows. What you end up with, and I'm going to use a big fat highlighter here to kind of show you, you end up with a general wind pattern that follows those curved paths. So all these winds are blowing, and we're talking compass directions now. They are blowing from the eastern half of the globe to the west. All right, they're blowing from the east to the west. Okay, that is an important thing. Back in the day, called these trade winds. Oops, man. Because this is what the old colonizer ships would get down into and hit these winds that would blow them towards their new colonies. So these trade winds come from the east, and they blow west. All right, so that's the big arrows that you see there. So the trade winds come from the east and they blow west. And here's the thing with winds. When we name winds, we name them from the direction that they come. So these would be what we call easterly winds, all right? Not because of the holiday, but because they blow from the east. So near the equator, you get these easterly winds where it blows from the east to the west. Okay? So we're almost done. We got just a couple more here to draw. We'll probably just draw the top one and go from call it good. Trying to get this one going there. Okay. So if we go back and take a look, at these arrows trying to go up right there, I'm gonna get rid of those. I'll go back to my pen. In this case, the air from 30 degrees north to 60 degrees north, if you follow the arrows, they're trying to go up. They're trying to go north like this, okay? Like so. But remember, everything on Earth in the northern hemisphere gets deflected to the right by the Coriolis. So even though the wind wants to go straight up, it gets deflected to the right, to the right, to the right, to the right. And remember, you always start at the end of the arrow and you go towards the tip of the arrow there. That's how you kind of orient yourself like, oh, which way do I go right from? Start at the end of the arrow and then go out like that. So, if you do that all over the place, doesn't matter where you are in that neighborhood, as long as you have wind moving from south to north there, it gets deflected again to the right. And so you get this overall direction of the wind that in this case, in this latitude, between 30 and 60 degrees north, you get these winds blowing that way, which is going from west to east. So up here, we have these winds that are starting in the west and they end in the east. So because they come from the west and blow east, we call these westerly winds or the westerlies. Okay? And so they come from the east. So there you go. And then if we're going at the polar regions, it's hard to kind of do the deflections in that small area. But again, it's going to be kind of a mirror image of that area down by the equator. And you get these deflections going that away, which comes from the east and blows west. So we call these the polar easterlies. All right. And so the polar easterlies, oh man, I totally screwed that up, didn't I? Huh. The westerlies come from the west. I just saw east there. So the westerlies come from the west. Let me fix that. It's late. I'm sorry. So those westerlies, the winds come from the west. They start from the west and they blow east. Okay. So they come from the west. And then these polar easterlies, they come from the east. But they actually blow west. All right. So that's kind of the thing that's kind of funny there. So the westerlies start from the west and they blow east. The easterlies start from the east and blow west. Okay. So anyways, we get this general flow. And if I were to draw that again, this general flow, the polar easterlies would be kind of going that way, like so. Alrighty. So what in the heck do we care? Well, let me try to zoom out here so you can see. Those flows would be basically the exact opposite down here in these other regions. So for example, to the left over here, to the left over there. So everything would be coming from the west, blowing to the east. So you also have westerlies here. All right, I'll say westerlies. And then you have polar easterlies down here too. And I'm not going to draw those because we don't have time right now. Okay, so there's our polar easterlies right down in there. So how does this relate to the real world? Well, I'm going to share a different screen here. Go back to there. We're not going to take a look at that anymore. I got to get that video off. Come on, go away. There we go. And what I do want to take a look at just really fast is this one. So I'm going to go up to where the air can more kind of freely flow, right around 500 millibars. And I'm going to tell you this right now. The atmosphere is in a very complex, wonky pattern right now. So I'm going to try to find you a better date that would better uh, exemplify what things look like. So let me see if I can go to maybe, let's go to August. There we go. All right. So the winds that you're seeing here from August, and you can also see a hurricane happening here. But if I go towards the equator, if you remember and look at the stuff, we talked about those easterly winds, those trade winds that blow from the east into the west. You can see there's a general pattern all around the globe of these winds blowing. Doggone it, where's my thing? Hold on. Trying to get my laser pointer. You can see them all blowing from east to west. So you can actually see those winds doing what we're talking about. And if you were to go a little bit further north, you get into the latitudes that we're in California, you can see that general flow, the general flow here is from west to east, right? So we have these westerlies. So this is why most of the storms that we get, when we get the storms, they actually are coming from the west and they blow into the east. And so that's a big deal when we start talking about rain shadows and things like that a little bit later on, like next week. So that'll help us explain kind of if we go down here, wow, why is there rainforest on the east side of South America and then dry desert on the other side of the Andes Mountains right here? But if I go down a little bit further, the pattern is flipped where it's green on the Andes side and or on the Chile side and deserty on the eastern Argentinian side. So we're going to try to figure that out next week. But on Friday, what we're going to do is figure out how do these high and low pressure systems, how do they spin up, and how do we start getting all of these tight spirals that, if we go to now, lead to this chaotic, massive mess. We're going to be able to make sense of these high and low pressures on Friday. So we're going to be drawing a little bit more there. Okay? So make sure you draw this. Make sure you add it to your drawings, kind of everything that we have there. That's going to be one of the major things we turn in for your sketch notes this week. And then on Friday, we got 2 other things to draw, and we'll go from there. Alrighty? Thanks for hanging in there. See ya on Friday. Thanks for letting me do this school thing for my son. Yeah, it's kind of a really important day, and so I appreciate it for letting me go asynchronous here. I'll talk to you later.